All right, there we go. Helps if the mic's on. All right, welcome to chemistry. I have no idea what happened with the stream. It wasn't just this stream, it was all three. So I don't know. I blame the internet. All right, let's go ahead and go to page 297 in our text, page 297 in our text, page 195 in your supplement, page 195 in your supplement. We need to finish talking about activity so we can get into some of the more fun stuff, such as the effects of radiation on matter. Yeah, fun. I use the word fun loosely in this class. All right, so we were talking right as the bell rang yesterday about how the half-life of a substance determines the intensity of the radiation it produces. The quicker it's going to decay, the more intense the radiation is going to be. Does that make sense? Okay. And so with that, we call this the activity of the substance. This is the amount of decay occurring in a radioactive substance at a given point in time. Substances that decay rapidly produce intense radiation that lasts for only a short time, high activity, whereas substances that decay slowly produce low levels of radiation that may last for eons, low activity. The activity of a radioactive nuclide, it's just nuclide, I don't know why I added an extra syllable in there, is measured by counting the number of nuclear disintegrations that occur per second. The SI unit of activity is called the becquerel, defined as 1 nuclear disintegration per second. If a sample of a substance undergoes 10,000 decays per second, its activity is 10,000 becquerels. Okay, pretty simple. It's kind of like Hertz, where it's cycles per second. Okay, so pretty easy to work with, except this is decays per second. So that's really the idea. You could word 10,000 as 10 becquerels because all the metric units apply. Because the becquerel is a small unit, an older unit called the curie is still commonly used. 1 curie is exactly 37 billion disintegrations per second, or 1 curie is equal to 3.7 times 10 to the 10th becquerels. Okay, the curie was made before the SI was really, I don't want to say mainstream, but kinda. Anyway, so before it was really widely adopted and like everyone just naturally did everything base 10, so that's why it's a weird number. But the curie does often get used, even though it's not an SI unit, just because it's a bit more convenient, much in the same way that we still use pounds. Okay, it's not necessarily convenient, but like everyone's used to it, so yeah, US. All right, USA. Okay, I'm moving on. Anyway, that's basically the idea. We're just stubborn. All right. Both units can be used to refer to an amount of radioactive substance. 1 curie of cobalt-60, for example, is the amount of cobalt-60 that would be necessary to provide an activity of 1 curie. Does that make sense? So we can say I have 10,000 becquerels of this substance. Even though that tells me nothing about its mass, it tells me how much radiation it's going to produce, which is also convenient. Just like we did with acids, we had normality, okay, instead of their molarity because it was more convenient in acids. Same thing here. Now, when an unstable atom undergoes nuclear decay, the new atom that results, called the daughter element or the daughter nuclide, may also be unstable, and in some cases, even more unstable than the original atom. These atoms will soon decay into still other atoms and so on until a stable nuclide is reached. The result of this process is a long series of radioactive nuclides ending in a non-radioactive or stable nuclide. Such a chain of nuclides is called a radioactive decay series. You may recall that all elements with an atomic number of 84 or higher are unstable to varying degrees. All these elements gradually decay, forming radioactive decay series that end with stable isotopes of lead. That's specifically where they mostly end up. All the naturally occurring radioactive heavy elements with Z is greater than 83 belong to one of 3 radioactive decay series. There's the thorium series, the uranium series, or the... Why did you hyphenate that? I mean, come on, it's 2 letters. Actinium series. Okay, sorry, it just makes it way harder when you're trying to pronounce the thing. The actinium series is also known as the uranium-235 series because it has a different path, and it follows that one more. So shown here, oh goodness, which one is this? This is the actinium or uranium-235 series shown in this graph, shown in the graph on your textbook, which was probably way easier to see than this one. I made these slides, these slides are the oldest slides because they're from the end of the book. So that makes sense, I promise. All right, anyway. The parent or original reactant nuclides in these 3 series, are thorium-232, uranium-238, and uranium-235, respectively. All these decays involve either alpha or beta emissions, some of which are accompanied by the emission of gamma rays. Okay, so anywhere it drops down almost drastically, you see that slope. Okay, that's where alpha decay is happening. It's losing 2 protons. Anywhere it has a jump up, that's beta decay because it just suddenly gained a proton. Technically, it didn't gain one, but you all understand what I mean. All right, so that's the reason for the jump. So notice it's alpha, then beta, then alpha, and then either beta then alpha or just alpha. It's weird, okay? There's a couple paths that could be taken there. So that's really what's happening there. So one of these series, the actinium series, is diagrammed in figure 17.13 on the screen. Notice that there are branches at several points that eventually rejoin the main decay series, ultimately reaching the stable nuclide lead-207. By comparison, the thorium series ends with lead-208, and the uranium series ends with lead-206. The time period given in each step represents the half-life of the parent element, the interval that would be required for half the parent nuclide in each decay step to decay to the daughter nuclide. Why is there an asterisk? Oh, yeah. Just quick mention here, one common misconception that gets used in radiation dating. Kinda. Radiocarbon dating is the word I'm trying to use. One common misconception that gets used is that everything had to start at the highest element. And so all the daughter elements we have are a result of that decay series. Okay. Where else on the periodic table is that true? You see the fallacy there? Because we have all the other elements, and they didn't all come from other elements, according to your theory, so why these? Okay? So we just believe that there was some of all elements created, and so on. Does that make sense? Okay, so that's the idea. Which actually makes perfect sense, but we're moving on. Other elements produce different radioactive decay series. Light elements generally do not produce long decay series, while super heavy elements typically have long decay series involving unusual nuclear reactions, in addition to ordinary alpha and beta decay. There's still a lot we're learning about those higher elements, by the way. Stable nuclei do not normally undergo nuclear reactions. However, certain types of nuclear reactions can be induced in a stable nuclei if the nuclei are bombarded with other atomic particles. For example, if a sample of stable cobalt-59 is bombarded with neutrons from a nuclear reactor, some of the neutrons will be captured by cobalt-59 nuclei to form radioactive cobalt-60. Cobalt-60 has a relatively short half-life, so there's not really a whole lot of it left around. But it's really easy to make. You fire a neutron gun at cobalt-59. That's actually the name for it. Yeah, it's basically like a shotgun with it's like a shotgun machine gun. That's basically how a neutron gun works. It fires neutrons in basically all directions repeatedly. So anyway. In this instance, an induced nuclear reaction has occurred that changed one form of cobalt into another. Left to itself, 59 cobalt would never have formed cobalt-60, but the reaction was induced by neutron bombardment. This is how we get cobalt-60 for cancer treatment. Cobalt-60 is extremely useful for treatment of cancer. So, hospitals that do a lot of cancer research actually typically have a small nuclear reactor on site. Small. Very tiny, to be clear. Okay. Because you need to create the radiation.
Wait, so nuclear reactors, so nuclear reactors have?
Nuclear reactors are anything that contains a nuclear reaction.
Oh, okay.
So it's not necessarily a nuclear power plant. There's a difference. We tend to just say nuclear reactor when we mean nuclear power plant. Nuclear power plants are large reactors with steam circuits and turbines and cooling tower, like whole different category of things. Anyway, we'll talk more about that later. A number of other particles besides neutrons can be used to induce nuclear reactions. These include alpha particles, protons, deuterons, which is hydrogen 2, and ions of other elements. Charged particles such as protons, alpha particles, and ionized atoms must have very high energies and thus high velocities in order to be able to approach and react with the positively charged nucleus of the target substance. By contrast, neutrons which are uncharged are not repelled as they approach the positive nucleus and may not need high energies to induce a reaction. It's really, really, really easy to get a neutron reaction to start, or neutron radiation to hit stuff, because they're uncharged, so they'll just go until they hit a nucleus. They don't care. All right, so Let me see here. Neutron radiation from specialized nuclear reactors is sometimes used to indicate nuclear reactions on an industrial scale, such as in the production of tritium or plutonium. On a smaller scale, particle accelerators, which use magnetic and electric fields to accelerate charged particles to energies of several million electron volts, may also be used to initiate nuclear reactions. In many hospitals, small particle accelerators called cyclotrons are used to produce radionuclides for PET scans and other medical procedures by the means of bombardment reactions. Oh, okay, yeah, so it's not necessarily they have to have a nuclear reactor. It's either nuclear reactor or a small particle accelerator. And I do say small because relatively it's small. It's still pretty big, but like, yeah. Then there's the Hadron Collider, which is the world's largest particle accelerator up in Sweden at the CERN facilities. Yeah. Actually, at one point, there was the possibility they could have created a black hole, and everyone's like, what are you doing? Stop it. Yeah.
Like just like really small.
Yeah. It's mildly terrifying. Moving on. Science. All right. Much larger particle accelerators can accelerate protons and other particles to billions or trillions of electron volts, enough to shatter protons and neutrons into their component parts, which is how we know about quark theory, or even to form new particles out of excess energy. We've actually created our own quarks that don't exist in nature, and it's really weird and it's really trippy, but also super cool. So, what are you going to do? Oh, sorry, I should probably have put that term up there. Yeah, particle accelerators are there. Let me see here. And there's a blue box that talks about the uses of radioactive nuclides. There's actually quite a few of them on page 299. From everything from cancer treatments to smoke detectors to PET scans. Actually, okay, a lot of this is medical procedures. Some of it's glow-in-the-dark stuff. It's really useful things. Pharmaceutical research, airport security. They got to power those X-ray machines somehow. Okay, so that's really what's going on there. So all the elements, for the record, by the way, just since I mentioned airport security, I should probably clarify what I mean. In the thing that your luggage goes through, okay, you'll notice there's a radiation symbol. Okay, because it's an X-ray machine, so it has radioactive nuclide in it to generate X-rays. As long as you don't go through the X-ray machine yourself, you're fine. Okay, that's why they tell you not to put your hand in there. That and, machinery. If you want to keep your hand, you keep it out. All right, anyway, basically, that's a whole different problem. All right, all the elements beyond uranium are called the transuranium elements. And these have been artificially prepared by the bombardment reactions, although some of them do occur naturally in trace amounts. For example, the bombardment of uranium-238 by a neutron produces uranium-239, which immediately undergoes beta decay to form neptunium-239. Within a few hours, this undergoes further beta decay to form plutonium-239, which is a lot more useful. Some of the heaviest transuranium elements have been produced by bombardment reactions using fairly massive particles, such as a calcium-48 atom. Table 17.5 gives reactions used to produce some of the transuranium elements. Both mass number and atomic number are conserved as we go through this. So that's really what's going on here. Basically, we can create all the elements higher than uranium by just throwing particles at it, because it's what we got. When in doubt in humanity, our main idea is to shoot something. I don't know why, but like, hey, here's an unstable element. Let's fire at it, see what happens. I mean, basically, like, I don't know. I don't know why that's our reaction, but it's actually useful in this case. So, all right, moving on. 17.4, effects of radiation on matter. As particles of radiation careen through matter, that's a great word, careen. All right, careen through matter, they may collide with electrons with such force that the electrons are knocked loose from their parent atoms, forming ions. For this reason, alpha rays, beta rays, gamma rays, X-rays, and neutrons are all ionizing radiation. This is any radiation capable of causing ionization. That's all it means. When most people say radiation, this is the kind they're typically talking about. Okay, I told you guys this is a very vague word. Okay, it's not typically just nuclear radiation, it's ionizing nuclear radiation. Okay, you all following me? Okay, so that's the key here. Commonly, molecules struck by ionizing radiation break apart due to the ionization of their constituent atoms. Although neutrons do not cause ionization directly, they do so indirectly by reacting with target nuclei to form alpha, beta, or gamma emitting isotopes. All right, so neutron radiation is not technically ionizing by itself, but usually the reactions it causes are ionizing. So, hence the problem with it. Similar ionizing effects also occur in living cells when they are exposed to radiation. Such ionization can damage the cell's molecular machinery or even cause changes in the cell's DNA, which contains the cell's genetic information. Although cells are designed with a surprising ability to repair radiation-induced damage, a high dose can overwhelm these systems and either kill the cell or cause irreversible damage. Cells are most susceptible to radiation damage when they are dividing or reproducing. Okay, that's what that means. This is why radiation tends to affect certain regions of the body more than others, okay? And y'all are near adults in here, so we're just going to talk about this real quick. There's a reason why the lead apron always covers a specific area, okay? If they get nothing else, they at least cover that, because in that region is where cells are dividing the most, okay? Because that's how reproduction works. This is not a biology class, so I'm not getting deeper than that. But that's all I'm saying there is there's a reason for that. You have to protect those cells because they're the ones undergoing division. Does that make sense? Okay? This is also why they try to protect your core, because your bone marrow, which, in case you haven't noticed, there's a lot of bones right in here, okay, is what forms your new blood cells. So they're constantly undergoing cell division. Does that make sense? But things like your lower leg, probably not undergoing a ton of cell division other than replacing current cells, so there's not a whole lot of damage that could possibly occur. Does that make sense? That's why the lead apron doesn't usually go all the way down. Cool? All right, so there's that. For this reaction, tissues containing cells that are not dividing, such as the brain and muscle, are less susceptible to radiation damage than rapidly dividing tissues such as bone marrow and the gastrointestinal tract. There's like your gastrointestinal tract is always being replaced. So that's why lead aprons typically go from neck, because thyroid, all the way down to about here, and then they're done, okay? Because that's the main region of you that, like, it's in danger. You might wonder why they don't protect your head, okay? Bluntly, with radiation, your head doesn't matter. And that sounds weird, that your brain isn't dividing, so who cares if it gets radiated? And that's super weird and trippy. It's like the one thing that the brain is like self-reliant on. Everything else, like, you got to be real careful with it. Radiation, it's fine. Anyway, so super weird. I mean, you still don't want a ton of it, to be clear, but like, All right, moving on. I'm getting off the track here. Where was I going with this? Oh, this is why radiation is useful against cancer, because cancer cells are rapidly dividing. They're rapidly growing out of control. Okay, that's what causes cancer to be such a problem. So radiation is really useful against that because they're in the middle of division, and that's when they're most susceptible to it. Okay, so this is why many types of cancers are treated by carefully directed radiation beams, because again, you don't want to get other regions. Okay, does that make sense? So we carefully direct the beams. I say we, the technicians carefully direct the beams. I have nothing to do with this. All right, so the various types of radiation differ on their effects on the body. Exposed to an external source of alpha radiation, such as dust contaminated with an alpha-emitting isotope, a person would experience little effect because alpha particles are unable to penetrate the skin. Again, unless you eat it, which you don't. It's not hard. Okay? A person would, beta-emitting isotopes can cause moderate to severe skin burns, called radiation burns, if deposited directly onto the skin, but such burns can be prevented by suitable clothing. Okay, honestly, even long sleeves is typically fine. All right, so, I mean, you don't want to just rely on that if you know you're going to be around it, but like, if you happen to be near some, oh well. The more penetrating varieties of radiation, such as gamma rays, X-rays, and neutrons, can pass right through the body's surface layers and tend to produce whole-body effects rather than localized burns. The gastrointestinal tract and white blood cells are particularly sensitive to penetrating radiation. However, alpha and beta emitters become far more dangerous if ingested or inhaled, whereas gamma and neutron emitters do not, because they didn't care about your skin in the first place. Okay? Here's kind of the danger of it. Alpha and beta emitters, they can't penetrate your... Well, okay, beta can penetrate the skin, but only barely. They can't really penetrate your skin to get in, but that also means they can't penetrate your skin to get out. So they just bounce around in there. Okay? And that's wherein lies the problem. Okay? That's why if you ingest or inhale it, it's now in your body unable to leave. So it's like a fly getting trapped inside. You know what I'm talking about? Where like it had no problem finding the door, but like it can't find the door again. Anyway, it's not at all annoying. All right, anyway, so same idea here with alpha and beta emitters. The other two didn't care about your skin in the first place, so even if you, I mean, you still shouldn't ingest it, to be clear. It'll do the same amount of damage because it could have already got it in, and it'll just go out. All right, so detecting radiation. The fact that ionizing radiation can knock electrons loose from atoms makes it relatively easy to detect. Instruments for detecting radiation may take several forms. You can see page 301 for a couple of, what's the word? Geiger counters. It wasn't in the caption, and I couldn't get the words in the captions out of my head. So we call them dosimeters, sometimes if it's a personal one, seeing how much radiation you've personally experienced. So they're all variants of Geiger counters, but we'll talk more about that in a minute. Some detectors use small gas-filled chambers to detect ionization, while others use fluorescent liquids or crystals, or even semiconductor chips now. Some detectors can even measure the energy of radiation, making it possible to determine the identity of the nuclide that produced it. Obviously, those would be a bit more expensive. Now, several units may be used to measure amounts of radiation exposure. All right, buckle up, settle in. This is going to take a minute, okay? Because there's a ton of different units, and the SI ones are not the main ones, because radiation is so new that no one agreed on a standard early enough, okay? So try to hang on. I'm going to do my best to just explain this. There's a summary chart on that page. You should probably study that when you're done, okay? It's a great question. Page 301. Page 301, table 17.6 has a summary of all this. I'm going to go through what we're talking about here. So, several units may be used to measure amounts of radiation exposure. The most common units, for many years, the most common units of radiation were of measure, hold on. Okay. The most common units of radiation measurement were the rad and the rem. The rad, radiation absorbed dose, hence the name, okay? It wasn't just because of the 90s. Just kidding. That was way earlier. Is the amount of radiation that caused an exposed object to absorb 0.01 joules of energy per kilogram of mass. Okay, it's a very small unit, but you got to remember, radiation, okay, in small units is fine. But you need to, like, it doesn't take much past that to start becoming dangerous. So we need a very sensitive unit. The rem is similar to the rad, but it takes into account the effect. Whoops. Oh, that's right. I went out of order. No, I have a reason for it. But anyway, I'm going to keep going in order of the book. You know what? I'm just going to do this. Cool. The REM is similar to the RAD, but takes into account the effects of different types of radiation on living things. Because the RAD and REM are rather large for measuring everyday exposure. Smaller, those are considered small. 0.01 joules per kilogram of mass is considered small for radiation. Or, sorry, large. Large for radiation. I said it backward. We need to use millirem and millirad most commonly. Among scientists, the older metric units, rad and rem, are gradually being replaced by the SI units, gray and sievert. A gray is 100 rads. It's 1 joule. So that way it's based on a single joule. It makes the math real easy. That's why people are going to the gray and sievert. Sievert is the same amount of biological injury as 1 gray of X-rays or gamma rays. Okay, typically the most common words you'll hear are rem or sieverts because they take into account the biological damage. Okay, and most commonly you will hear the term millisieverts. If you hear a unit given in sieverts, you're already dead. Okay, just to be clear, unless the decimal is really tiny. Okay, you're really hoping it's millisieverts. Okay, just FYI. Table 17.6 gives it, but we're going to talk about, oh goodness, that's right. In the book, they do everything in rem. Okay, I'm good. All right, so I'm going to talk about everything in rem because that's what the book does, and I don't feel like converting everything. You could look up all the values for sieverts. It's the same amounts, just different units, okay? All right, so let me give you guys some context for radiation dosage so that way you guys can be familiar enough with it so that you guys don't, follow the masses and induce panic when anyone talks about a radiation leak. We good? Okay. The average American receives between 0.3 and 0.4 rem per year, mostly from natural sources. Again, some of it can be from smoke detectors. I mean, minor, okay? Really not a whole lot. Now, this number actually does go up slightly if you're in a high-efficiency home because the air gets recirculated more. Because the air gets recirculated more, any radiation that was already in the air hits you more. Does that make sense? So while it's great for your heating and cooling bill, it does slightly increase your exposure to radiation. However, not significantly and not enough where you should care. Okay, just letting you know that number can be slightly higher. This number also depends on where you live. Okay, for example, if you live right next door to a power plant, this might be a tad higher. Seriously, not much. They're really well shielded. We're going to talk about that. Okay, or if you're just near a natural source of radiation, it's going to be a little higher. Okay, but this is all perfectly safe. Temporary harmful effects such as changes in blood cell counts occur in exposures between 10 and 50 rem. So notice that our average is way under when damage starts to actually occur. Okay, our body is used to handling this type of radiation because we're around it all the time. I mean, we're designed, like the planet is radioactive, the sun is radioactive, you are radioactive because you have some carbon-14 in you. That's just how that works. Okay, your friend sitting next to you is radioactive. Okay, like that's just how this works. Yeah, the table next to you isn't radioactive then. Okay, fine. Does that make sense? Like again, to an extent, a very small extent, a very tiny amount, but it's true. Does that make sense? So people throw around this term radiation without any context to what it means. So yeah, you get between 0.3 and 0.4 rem per year. Not a big deal. Okay, really not. It doesn't start to become harmful until about 10 rem. Okay, which, you're well under a tenth of that, so you're good. Okay, even if you're occasionally get an x-ray, you're fine. Okay, by the way, that average does account for the getting x-rays, PET scans, and so on. For some people, that number obviously would be higher if they get way more medical treatments. Okay, moving on. Radiation sickness. Okay, by the way, temporary harmful effects are things where you just might start feeling a little bit weaker. That's basically it, and then the body will recover. Okay, that's why it's temporary harmful effects, hence the word. Radiation sickness, when you really should start to be hospitalized, really begins to occur at exposures of between 200 and 300 rems, somewhere in there. Okay, so you get those temporary harmful effects where you're going to feel fatigued, you're going to feel exhausted, your body's going to basically feel like it's fighting a stomach flu a little bit, and that's going to happen, around 10 to 50 rems, somewhere in there. But past that, give it a few days, shake it off, you'll be fine. Okay, radiation sickness, on the other hand, you'll start feeling very ill. Okay, it won't just be an upset stomach; you'll actually be vomiting, and so on. All right, severe radiation sickness, along with a 50% chance of developing cancer, occurs around 400 rem. Okay, you can see that this is starting to escalate pretty quickly. Whole body exposures of 600 rem are usually fatal within 30 days. Okay, you can kind of see this is almost logarithmic. Okay, the body can deal with radiation pretty well, actually, but there's a limit, just like anything else. Okay, like your body can metabolize a certain amount of, okay, I'm just going to use the example, don't do this, as a certain amount of alcohol and you'd be fine, but you can't actually drink yourself to death. Okay, seriously, don't drink, don't get involved in it. I've watched too many family members, not immediate family members, but I've watched too many people just drink themselves to death. It's not pretty, just don't do it. Anyway, that's my whole thing with that. Anyway, so this is really kind of the chart, if you will. Personally, I like to use millisieverts because it's what the rest of the world uses now. But I forgot to write them in, so we'll come back to that later. But the main thing I want you guys to take away here is notice how much you naturally get, and I always talk about this. Okay, you always get some naturally, and then yeah, it takes a whole lot to actually kill you through radiation. So it sounds like this big scary thing. The biggest reason why it's scary is because it's invisible. Because we can't see the immediate danger. And so you could walk into a cloud of radiation and not be aware of it. Okay? That's the part that makes it scary. But again, we have devices for that. So if you think you're going to be even remotely at risk, you wear one of those devices, it'll let you know. Okay? Really simple, straightforward stuff. But as far as your day-to-day, you don't have to be concerned about your radiation exposure. Even your medical procedures. I mean, these REM amounts, we're talking about a single exposure. We're not talking about over the course of the year. So even if over the course of a year, you received 3, 4, 5 REM because of medical procedures, you're still well under where you'd have to be concerned for radiation. Does that make sense? Okay. So a couple things I want to point out and make a conclusion of with this before ending this week's lectures is simply this. Nuclear radiation is not artificial or the result of 20th century technology. Most modern forms of it is. I am fully aware of that, but nuclear radiation itself is not. See the sun. Don't look at it, actually. That's bad. But anyway, just for reference, the sun, or the fact that uranium is around and in the earth where we can mine it. You following me? Okay, it's not a new thing. It's not an artificial thing. It's not something that we just decided to meddle in. I mean, it kind of, well, moving on. It's not something we created, okay? It was entirely a natural process, but like many natural processes, we figured out how to work it to our advantage, or sometimes our disadvantage, but we're not getting into that yet. All right, does that make sense? Okay, so that's the thing I want to leave you with. Also, about 75% of radiation experienced by Americans each year are from natural sources. The other 25% would be things like medical procedures, things like, actually it's mostly medical procedures, to be honest with you. Most of that other 25% is medical. Obviously, it depends on where you live in the U.S. It also would depend on you living in the U.S. If you don't live in the U.S., these numbers would be slightly different. All right, that's it for this week. I did hear the bell, so I'm going to let you guys go here in just a second. I'm sorry. You guys do have quiz 17, which stops at 17.3. You don't need to know all the REM and millirem stuff, okay? So that stops at section 3. We'll take that quiz tomorrow. If we have enough time in class, we'll watch the next video. Otherwise, we'll start Monday with that. And Monday, we'll get into 17.5, which is honestly the most interesting section in here. All right? I'll see you guys later.
All right. We're going to get started. We're on page 366, section 12.4, ratio analysis. Ratio analysis. Since ratios show the relationship between two items, they are often used by business management to analyze the financial position of the business. Two business ratios used to measure the liquidity of an asset are current ratio and quick ratio. Okay, again, liquidity is just the ability to turn that asset into cash money fast. Okay? Both ratios indicate the business's ability to pay its bills. The current ratio is found by dividing the amount of the current assets by the amount of current liabilities. As a general rule, a current ratio of 2 is a sign of good liquidity. Okay? So we have model problem number 1 here. Likes Candy Store has current assets of $12,650 and current liabilities of $4,890. Find the current ratio to the nearest tenth. So we have current assets over current liabilities, and then we divide that out, and you get a current ratio of 2.6. Okay? The quick ratio, also called the acid test ratio, is the relationship between the most liquid current assets, cash and accounts receivable, and current liabilities. The quick ratio is found by dividing the amount of cash plus receivables by the amount of current liabilities. A quick ratio of 1 is a good sign of liquidity. So you have cash and receivables over liabilities. And we have model problem number 1 here. Number 2, find the current and quick ratios for the business whose balance sheet is shown below. Find each answer to the nearest tenth. Okay, again, tenth is 1 decimal place. So we have the current ratio is current assets over current liabilities. Assets are $10,240, and current liabilities are $2,850. Do the math here, divide it out, and we get a current ratio of 3.6. Do the quick ratio. We have cash plus receivables over current liabilities. So we have receivables or cash of $600, cash in the bank of $3,400, accounts receivable of $980. We're going to add that up to get $4,980. And then we have current liabilities of $2,850. Divide that out, and we get a quick ratio of 1.7. Okay? So the key here is current ratio is current assets over current liabilities. The quick ratio is cash and receivables over current liabilities. Divide it out. For current ratio, you want around 2. For quick ratio, you want it around 1. Okay? And we're going to go ahead and do problems 1 through 10 for homework. Don't forget, you guys have a quiz tomorrow. That is over sections 12.1 to 12.4. Okay, that's all we're going to be doing in class tomorrow is that quiz. Volleyball team, I'm not sure what time you're leaving. I believe your game is at 1, so you might not be here for the quiz. All right, so you'll just make that up on Monday. All right, I'll get the homework on Google Classroom here in just a second.
All right, in your grammar book, turn to section 29, page 120 in your handbook, dealing a little bit more with words we should use in our writing, exactness and vividness. Basically, just talking about words that you can use better. Yesterday, we talked about appropriateness, avoiding, obviously, non-standard or substandard words in our talking and writing. Depending on what we write, we can use either standard formal or standard informal. And talking to each other, obviously, standard informal. But with papers and different things like that, important documents, important emails, if you're ever working in a company that you send emails back and forth to your coworkers, probably you would use standard formal English. Okay, so this section we are learning about exactness and vividness in our writing. All right, let's look at 29.1. One thing to avoid is improprieties in writing or speaking. Okay, improprieties are standard words used incorrectly. So basically, when you're talking and you're using a word, but you're using the wrong form of the word. Here's your examples. Okay. They were mighty proud of their trophy. Okay, mighty is an adjective that is in this sentence being used as an adverb here. That's incorrect. It should be especially proud. Okay, the blockers defensed well on that play. Okay, just by looking at it, what should it be, class? Defended well. Okay, you can't defense well. That is a noun, and you can't change it to be a verb there. You defended well. And then the last sentence, the mayor met with some members of the city council. Okay, notice how the wrong form of council is being used in this sentence. Okay, the sentence or the word that they use in this sentence, who knows what that council is referring to? COUNSEL. Anybody know? Like, what is that form of a council being, like, what does that mean? COUNSEL. Yeah, like give advice, okay? It should be COUNCIL. Council is like the board of leaders or a board group, okay? So that is what improprieties are. If you're using one word, but you're using the wrong form of the word. Okay, improprieties often occur when a word is confused with another word similar to it. Okay, following is a list of words which are often confused. Okay, look at your first examples. Advice, okay, versus advise. What do you think advice is, class? Advice with C-E, A-D-V-I-C-E. Does anybody know what this advice is talking about? Okay, advice is like something you get, okay? Something someone tells you. It's like the same thing with counsel, okay? Advice there. Advise here is a verb. You are actually doing advising. Like advice with a CE is the noun, something that you get. Advise, A-D-V-I-S-E, is something you give, right? You are advising them in their finances, okay? A financial advisor, something like that, okay? What about alter, A-R, and then alter with an E-R? What is A-L-T-A-R, class? It's like the front of a church or a sacrifice or something like that. What does it mean to alter, A-L-T-E-R? Like change, okay? So that's kind of what is going on with improprieties. You're using the wrong form of something that you mean, okay? And in this section, obviously, it's something to be careful of because you don't want to sound uneducated. You don't want to sound like an idiot when you're using the wrong form of words, right? Look at this. Alumnus and alumna, okay? What is an alumnus? Okay, someone that has graduated and has, right, singular form. Okay, What is an alumna? Alumna is basically referring to a female alumna. So the differences between those, okay? Alumnus obviously is, we don't know the gender, or it's a guy. Alumna is a girl. So alumni obviously is plural, okay? But just the different things like that, okay? Alumni and alumnae, the differences between that is like, it's the plural form, but the correct one is alumni, not alumnae, okay? What are the differences between capital and capitol? What is AL, class? Okay, capital letters. Okay, like money, or like the capital of a state or a capital of a country, right? What is capitol? CAPITOL. Who knows?
That one's money, right?
No.
No?
I don't know. Capitol is actually referring to a Capitol building. Okay, Capitol is when you would go to like Sacramento and you would see the Capitol building there. Capital is referring to money, referring to a city, referring to a capital letter, Michelle. Okay, so that's why, because if words are so complicated, it is complicated, but if you have everything spelled the same way, how are we supposed to know the definition? Okay, well, what would you use for a different word there? Then that would be even more complicated. There's even more words to memorize, okay? The differences between cite, C-I-T-E, or cite, S-I-T-E. Class, we all should know what C-I-T is, and that's what? Okay, to give credit to something. Everyone should know what that is, since we all have a works cited paper for our research paper. Okay, what is cite, S-I-T-E? It's like a place, okay? The next one, compliment and complement, okay? What is the one with the I? Exactly, you're complimenting their shoes, you're complimenting their hair, you're giving them some kind of good comment, okay? What about compliment with an E? Okay. Something to remember, the differences between those is complement with an E is basically you're completing something that's complementing something, completing, okay? Compliment with an I is I'm giving you, a compliment, all right? What about dying, D-Y-E-I-N-G, and then D-Y-I-N-G? What's the first one with an E? Like tie-dyeing, okay? And then dying, obviously without an E, would be death. Okay, so the differences between those, emigrate and immigrate. Obviously, immigrate is to go, travel. Emigrate is to come. It's like someone or something like just to travel to a place. Immigrant is like going out and then, hold on, let me just give you the exact definition of it. I don't want to confuse you. But emigration or emigrate is to leave your country and then to settle permanently in another. Immigrant is when you're coming into a country. Does that make sense? So if people come to America, they're immigrants. The country that they're leaving, they're emigrating from that country. Okay? Hoard and hoard. No, the difference is like just hoarding stuff in your bathroom. A hoard of maybe like cattle, a bunch of people, a bunch of, I don't know, like a tribe, like a horde of tribe. Those are like differences between those. Illusion and allusion. Illusion, something that has to deal with, our sight, and that's kind of trippy. Allusion is like we're referencing back to something. Imminent and eminent, loose and lose, principal, principal, and then roll and roll. Okay, roll as in the part you're playing, roll as in to tumble. Okay, so that's what improprieties are. Make sure you're using the correct term or the correct word of what you mean. 29.2, make skillful use of connotations. Okay, a denotation is basically a word that by its definition, it's the strict definition of a word. Okay, this is exactly what it means. connotation, in that the way that it's different from a denotation, is that connotation is based on how you're using it and what you may mean. So denotation, you're like, okay, this is what the dictionary says, this is exactly what it is. Connotation, it might have a different meaning. For example, okay, the denotive meaning of the word democracy is a government in which the people hold the ruling power. Okay? But in America, democracy can refer to a government. It could refer to anything that has to do with the Constitution. It has to deal with the people ruling, but it's not the exact definition. To democracy may mean different to you other than its strict dictionary meaning. Okay? So one way to remember that is denotive is D, obviously, for dictionary. Connotative is the opposite of that. You could use the words what you may mean, and it could mean something different for you. Okay? 29.3, choose exact and vivid verbs and nouns to make your writing interesting and forceful. Okay? Here's what they mean. Letter A, choose verbs with action and color to create mental pictures in your mind. What this means is, rather than saying he ran to the store, okay, you can use different words like he hurried to the store, a picture in your brain that he was in a hurry and he was, running, or he was going as fast as he can. For example, the stream flowed, okay? The verb flowed is a general word that doesn't show any specific action. Yes, it's flowing down the river, but is there parts of the river that it was gushing? There's parts of the river that it was swirling, splashing, gurgling, just vivid words and nouns that can make your writing so much better and come alive. Letter B, wherever possible, use exact and vivid verbs instead of verb-adverb combinations. For example, your sentence may be, the dog lay carelessly on the floor. Okay, my verb is lay, carelessly is my adverb. You can, instead of saying that, you can say the dog sprawled on the floor. Again, another word, he ran quickly from the room. Okay, he dashed from the room. He sprinted from the room. Okay, just exact verbs that convey what you mean. Letter C, learn to select specific nouns rather than general nouns. In the following examples, notice the progression from general to specific, okay? So for example, the word game, all right? Obviously, we would need to read the context of the sentence in order to know what it means. But in this sentence, it's referring to when you're hunting, okay? Game, all right? You're hunting fowl, specifically what kind of quail, okay? What kind of fowl? Quail. What kind of quail? A bob white quail. Notice how it's from general to specific. Lumber, okay? General term, obviously we know what lumber is, comes from trees, okay? But what are you using the lumber for? Hardwood, okay? Tropical hardwood, specifically mahogany, all right? Food, obviously food can be hundreds and thousands of denotive or a noun, anything it could be, okay? Specifically meat, specifically what kind of meat? Beef, okay? What part of the beef? Sirloin. Notice how it starts from big and then it goes to small, specifically what you mean, okay? In letter D, something that might help you with your writing is look up for synonyms, okay? Synonyms of nouns. We know what synonyms are. They are words that mean the same thing, but rather they may give you a more specific noun there, or a more specific verb that you could use. Something that means the same thing, but a vivid noun or verb. Okay? 29.4, use exact and vivid modifiers to enhance the verbs and nouns you have chosen. For example, adjectives and adverbs, no matter how vivid, can never make up for poorly chosen verbs and nouns. But they are often necessary for preciseness in description and for subtle shades of meaning. So, even though you are using crazy adjectives to describe a general term, sometimes that might not make a difference in your writing. So choose exact and vivid modifiers. Letter A, carefully select the adjective needed to express your idea. For example, the following words are synonyms, but notice the slight differences in meaning. Okay? Witting, amusingly clever in perception and expression. Facetious, clumsy, or inappropriate in attempted humor. Jocular, sustaining a jolly mood to help keep others amused. All of those are synonyms. They may describe someone who is funny, but exact and vivid nouns you can use for what you mean, okay? Letter B, make good use of participles. Class, we've already studied participles. What are they being used as? Adjectives. Participles make especially colorful adjectives. For example, the sound of the crackling fire and the smell of the bubbling stew lifted the spirits of the cold and weary hunters. Okay, just by reading that sentence, I know that you can almost hear the crackle in the fire. You can almost see that the stew is boiling, right? Because their uses of description or participles is pretty exact and vivid, okay? Letter C, be sparing in the use of adjectives, okay? This one, you don't want to always be like the good, polite, blah, 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 and then finally get to your noun, right? You can be sparing, okay? We listened with delight to the sweet, pleasant, agreeable tones of the harp, okay? That's too much there. All right, but there's another word that you can use that means all three of those. We listen with delight to the dulcet tones of the harp. Okay, letter D, use the most vivid adverbs you can find. Adverbs that end in ly are usually the most vivid. Okay, foolishly, benignly, menacingly, agilely, fastidiously, jealously. Okay, vivid adverbs there. Letter E, carefully select the exact adverb needed to express your idea. For example, the word slowly is a general word. You can use the word crawled, okay, or leisurely, deliberately, gradually, reluctantly, hesitantly, sluggishly. Anything else besides that? And then letter F is something to really note here. The words very and really are greatly overused. So, as often as possible, use something else besides the word very, okay? They decidedly, extremely, exceedingly, incomparably, indeed, okay? Actually, especially, different words besides, yeah, we were very tired, okay? Use words like we were extremely tired, or this food is really good, okay? You can say, this food particularly is good, okay? Just words to switch up your vocabulary, all right? In your book, on page 60 in your workbook, okay, go ahead and turn to page 60, exercise 112. That will be tonight for homework. And what you're going to do is you're going to look in your workbook at 29.1, the differences between the two words that we went through. Okay, we didn't go through all of them, but we went through the left-hand side. So what you're going to do for homework is to write a sentence using any, let's just do any 5, okay? You don't have to do 10, but using correctly any 5 of the words listed under handbook section 29.1. So you're going to write an example of the word hoard, H-O-A-R-D, and then you can write another example of using the word H-O-R-D-E. So you're going to have to, it's going to take a little bit of work. You're going to have to look probably up the definition in your phone if you don't know what it is. Okay, but writing 5 sentences using correctly the given words here. Okay, so page 120, 29.1 in your work or your handbook, page 60, exercise 112 in your workbook. Okay, all right, so that's for your grammar homework tonight. Also, make sure you are studying for your unit test tomorrow, okay, in literature. Does anybody have any questions over that? All right, we're just going to review a little bit for that. Okay, let's go through our authors. Okay. Yeah, that's fine. Okay, who wrote Ode to a Grecian Urn? Who remembers that one? Okay, we're raising our hands. eraser that I could borrow real quick? I don't know where my pencil went. Like an eraser? No, like just the end of your pencil. That's all. Oh, awesome. Thank you. All right. Ode to a Grecian urn. You can raise your hand and tell me, Emma. John Keats. Good. Who wrote, who wrote Rondo? Who wrote Rondo? Good. Leigh Hunt. Okay. Who wrote Pride and Prejudice? Esther? Jane Austen. Who wrote Brightest and Best of the Sons of the Morning? Michelle? Reginald Heber, I believe his name is. Who wrote Abide With Me? Abide With Me. Ian, do you know? Abide with me, abide with me. Emma? Light, good. Okay, that's on page 315. Who wrote Praise the Savior, praise the Savior. Esther? Thomas Kelly. Okay, those are a part of obviously the hymns that were written during this day. Ivanhoe and Rebecca, that was a novel during the Romantic era. Yes, Noah? Sir Walter Scott, good. Dream Child, Reverie. Esther? Charles Lamb, good. Let's see. Did I have you guys know 2 things from John Keats? Just from, I'm not sure because I have it marked, but I didn't know if I gave you When I Have Fears. Did I give you guys that one? When I Have Fears? Yeah. All right, so class, who wrote When I Have Fears? John Keats. Good. What about the Childe Harold's Pilgrimage? The Childe Harold's Pilgrimage. Ian? Good. Okay, George Gordon, Lord Byron. Who wrote The Battle of Blenheim? Tori? Good. Robert Southey. Who wrote The Rime of the Ancient Mariner? Rime of the Ancient Mariner. Class, do we know that one? Samuel Taylor Coleridge. Remember, that was the one where it was kind of like the really long dialogue between 2 people. It was kind of like a play. Who wrote To a Sky-Lark? Who wrote the first To a Skylark? Emma? Wordsworth. And who wrote the other To a Skylark? Shelley. Okay, make sure you know the differences between those 2. Who wrote She Dwelt Among the Untrodden Ways? She Dwelt Among the Untrodden Ways. Class? Wordsworth. And he also wrote the one where it mentions the daffodils. Class, which one's that one? I Wandered Lonely as a Cloud. Good. Okay. Give me one thing that the Bible influenced the people. How the Bible influenced the people. Purified their thoughts, refined their minds. Okay, what else? Oh, refined their language. What was it, Michelle? Responsibility, a new sense of responsibility and importance. Good. There's one more thing there. What was it? Okay, yes, it kind of gave them a love for nature as a creation of God. But because they knew that God created nature, what religion did they tend toward in this era? Jaylene, do you remember the religion that they had during this era because they loved nature? Pantheism. Good. Okay. Give me the Lake Poets. Lake Poets, class. Wordsworth, Coleridge, and Southey. Okay, Wordsworth, Coleridge, and Southey. Give me one type of novel that was produced during this age. One type of novel. Esther? Okay, the historical novel. What else? Christian? the Gothic novel, and then the certain type of novel that was perfected by Jane Austen. Who remembers the last novel? Isaac, do you remember? It's a novel of something. Noah? The novel of manners, okay? Let's see. Who was the greatest English poet since Milton? He also was the world's supreme poet of nature. He really, really worshipped nature here. Victoria? The greatest English poet since Milton. Good. William Wordsworth. Let's see. Class, who were the lake poets again? Wordsworth, Coleridge, and Southey. Good. What is the greatest of all English literary ballads? Greatest of all English literary ballads. Kylie, do you know? Emma? Tori, do you know? Grace, do you know? Class, what is it for those of you who do know? The Rime of the Ancient Mariner. That is the greatest of all English literary ballads. Okay? Remember, ballads were like kind of like the songs that they did back then, and it was introduced a few units ago, but this one was the greatest of all English literary ballads. Who was one of the finest English poet critics? Poet critics. He was also one of the lake poets. Tori? Coleridge. He was one of the finest English poet critics. Remember, he was the one who wrote what, class? Rime of the Ancient Mariner. Class, what did Coleridge write? The Rime of the Ancient Mariner. Good. Okay. Let's see. We know Robert Southey. He wrote The Ballad of Blind Hen. George Gordon Lord Byron was one who wrote some poems here. Who was the greatest English lyricist? The greatest English lyricist. Michelle? Good. It was Shelley. He was the greatest English lyricist. That's on page 280 if you haven't marked that. Page 280, the greatest English lyricist. Okay. Remember, he was the one that wrote To a Skylark. Okay, without the dash, kind of following after Wordsworth. All right. What is the most famous ode in English? Famous ode in English. Class, what is it? Ode on a Grecian urn. That is, or Grecian urn, page 288. Page 288, okay? The greatest or the most famous ode in English. Written by who, class? John Keats. Good. What is an elaborate French verse form which usually has 15 lines? An elaborate French verse form which usually has 15 lines. That's on page 290. Everyone turn to page 290. Class, all together. Rondeau. Okay, or rondeau. That is an elaborate French verse form which usually has 15 lines. Okay. What type of novel deals with the original mystery and horror story, class? The Gothic novel. We're now on page 293 if you haven't marked that. The Gothic novel. There are three types of novels. Obviously, we said the Gothic novel, the historical, and the novel of manners. Okay. The Gothic novel deals with the original mystery and horror story. Okay. Which novel sought to show the spirit of a past age? Class? Historical novel. Obviously, history is something that happened before. So that one should be pretty easy to identify. Historical, past age. And then the last one dealt with social customs and manners. Class would be a novel of manners. Okay? Pretty easy to remember. Who wrote Ivanhoe and Rebecca? Sir Walter Scott. And what kind of novel did he perfect, class? The historical novel. All right. Sir Walter Scott perfected which novel, class? Historical. That's on page 299. He was the creator of the historical novel. Okay. What is the first significant novel to deal with an entire family? Tori? Pride and Prejudice. How many of you guys have seen the movie? How many of you guys have read the book? It's a really, really long book, and it's a really, really long movie. I'm talking about the one with Keira Knightley, but the old one and the new one is really long as well. Yeah, it's super long. I do like Pride and Prejudice, but it is really long. Who refined and simplified? She refined and simplified English poetry, making it a true reflection of English life. She was one of the first novelists to chronicle the lives of everyday, commonplace people. Something that we could probably do the process of elimination, since she's probably the only woman author. Class? Jane Austen. That's on page 307, okay? She just refined and simplified English poetry, dealing with the novel of manners. Kind of makes sense because she perfected the novel of manners during this time. Okay. Charles Lamb wrote The Dream Child of Reverie, which is a familiar essay. We know that during this time there were hymns that were produced during this age, which brings us to Abide With Me, which was written by who, class? That's on page 315. Good. Henry Francis Lyte. Okay, so he wrote Abide With Me. This hymn was based on Luke 24:29. What did Thomas Kelly write, class? Praise the Savior. Okay. We know that Reginald Heber, he wrote The Brightest and Best of the Sons of the Morning, just different things like different hymns that were produced during this age. Okay, so that'll be for your test tomorrow. Make sure you're reviewing, studying your authors, and just different parts of the Unit 6. Okay, and then go ahead and also write your roots, your prefixes, and your suffixes twice tonight. And then that'll be it for today. So page 60, those sentences, just 5 sentences, roots, prefixes, and suffixes twice, and then review for your test. Okay, any questions? Make sure you guys are working on your final draft. If you have any questions, let me know. And then, Christian, I will give you that tomorrow, first thing, okay? Sorry about that. All right, you guys are dismissed.